So quiz tomorrow is only on chapter 8, and chapter 8 is only on exams 4. All right, only exams 4, but you can look at the key just to sort of see which exams those are. Student asked about this exam. This is exam 4A in fall 2020. They wanted me to do these two questions, 21 and 22, which are a type of question that you'll see on the quiz form. Yeah. This is the exam 4A, fall 2020. 4A, fall 2020. The first one, just want to find the moment of inertia for this system. The axis of rotation is here, and so anytime the axis of rotation is outside of the object, you're always going to be doing this I is the sum of mr squared. I would say also that if you have multiple particles or multiple objects, but that's not always true because sometimes you're finding the moment of inertia for two objects like a disk and a bar that come together. You've probably seen questions like that. We'll see one before we leave. But definitely, if the axis of rotation is outside of the object, that is always a collection of particles. As opposed to being internal to the object, the axis of rotation. So here I want to know the sum of mr squared. I don't give you r, so you have to figure that out by recognizing that this is a equilateral right triangle and that each of these sides are 2 meters and 2 meters, right? Because the side of that square is 4 meters. So that means that the hypotenuse of that, which is going to be the square root of 2 squared plus 2 squared, that's the square root of 8, is 2.8, so this is 2.8 meters. Then the mass is 2 kilograms, so I is going to be the sum of 2 kilograms times 2.8 meters squared, but there are 4 of them, so I'm just going to multiply that times 4. So I get 8 times 2.8 squared, and that gives me 63. So that's equal to 63. So that's the moment of inertia for that system. And then in the next question, which was carry on to that, I have this force that's acting, and I want to know what is the net torque on that system. So to find the net torque, well, I know this distance is 2.8 meters. That would be the moment of inertia, right? There's not a clear moment arm on this. Like there's not an object that goes across that length, but that is the moment of inertia, that distance from where the force is applied to the axis of rotation. So the torque then is equal to Fr sine theta. Theta here is that angle, that's 90 degrees. I'm just going to leave that off because it's equal to 1. So that's equal to 5 newtons times 2.8 meters. That's 10, 4, 14? Yeah, 14. B is the right answer. I think that was the only ones that they wanted me to look at. Let me double check. Yeah, 21 and 22. Go on though, there are other questions where I could go on and I could ask, what is the angular acceleration? And in this case, I would say that it's torque over I. That would be 14 Newton meters divided by the moment of inertia, which was 63. And so that would give me 0.22. That's in radians per second squared. And then if I wanted to know something like omega or theta, omega would be equal to alpha t, theta would be equal to 1/2 alpha t squared, and I could find one of those quantities for a given time. That's not what this question was asking, but there are other questions that ask similar outcomes. Okay? So the quiz, you're in a moment of inertia. I'm going to ask you one of those. I'll probably ask you a ranking question too regarding either moment of inertia or torques. We've done several of those in class. Probably seen them in the exam. Also, you'll have to find the net torque acting on a body. There'll be multiple forces. One or more of those forces will actually create a torque. You have to determine the net torque. You'll probably also have to take that net torque and a moment of inertia and then find an acceleration, kind of like we did here. You'll need to know how to do angular momentum problems. That is where I have two objects that come together and rotate at a certain speed, and one object that changes this moment of inertia, and you need to find out what its new angular speed is. You'll need, let's just sort of take a look through this one. think that's, oh, and then energy, the kinetic energy and the work energy. There is no, well, no, I'm not sure that's true. Never mind. Yeah. All right. What questions do y'all have? Particular questions? Yeah, Tyrese?
Number 1,
Call 23, number 1. I think this is backwards, this file. Is my file backwards by date? It is, isn't it? Oh, that's unfortunate. Oh, poopy, I don't think I have 23. Do I have 23 in this file? This is the same file. It's the first one, okay. So, number 1. Okay, yeah, so this is a problem that's similar to what we did in class, except where I was adding the translational kinetic energy and the rotational kinetic energy, except here, when the mace, you know, it's spinning, and then when it comes up into it's spinning and it has some height. You all seen a mace before, like where they throw it up in the air, or a baton, or something similar to that. So when it's at the top of the trajectory, it's spinning, but it doesn't have any translational velocity. However, it does have potential energy. So if I want to know the total energy of the mace, it will be equal to the rotational kinetic energy plus the gravitational potential energy. I said we haven't done one exactly like this, but we did one where we added the translational and the rotational kinetic energy. This one's very similar. So that's going to be 1/2 I omega squared plus m times g times h. Then we need to go about and determining all those various values. So the first thing I want to know is what is the moment of inertia for this? This is a bar or a rod, and that's equal to 1/12 mb squared. Again, axis of rotation is internal to the object. It's in the middle of it, so I know that that is an object. And I give you the mass. It is 3 kilograms, and it's 2 meters long. Conveniently, it's just equal to 1 kilogram meter squared. So that's going to be equal to 1/2 of 1 times omega. Do I give you an omega? Oh, I do. I tell you the angular velocity right there is radians per second. Look, knowing the units of all these variables will really help you to be able to identify what those things are. Here I tell you specifically that it's the angular velocity, but also knowing the units of each will help you. So that's 1/2 of 1 times 4 radians per second. That's squared, plus the mass, which is 3, times g, which is 10, times h. It says it goes up to a height of 5 meters, and then that gives me 8 plus 30, 150, 158, or 160 joules. That's okay, Tyrese? Probably going to have one where you have to add up 2 different types of energy. Pretty sure about that.
So B is the total length?
B is the total length, that's right. It says that on that table. It has text that describes each of those things, but B is the total length, R is the radius, M is the mass. I think those are the only quantities you have. What else, Joe? Yeah, Tyrese?
Number 5, what is the same again?
Number 5? Okay. There really isn't any problem that you're not going to see that you've had on past exams. Yeah, this is another good one. So you have this potter's wheel, definitely going to have one like this too, where I have this object that's spinning, and then somehow it changes its moment of inertia, and I want to know how it's going to spin now. So if I had this potter's wheel, you know what a potter's wheel is, right? Like this wheel that spins, you put clay on it, you can form it into whatever. In this case, the potter's wheel looks like this, and it's spinning around, and then we come along and we drop a piece of clay on the edge of the potter's wheel, which isn't where clay is supposed to go on a potter's wheel. I get it. Like my daughter, she does pottery. It should go in the center, right, where it doesn't change the moment of inertia at all. But in this case, they throw it onto the edge, and it makes the moment of inertia go up. So I want to first find out what is the initial moment of inertia. Well, I tell you what that is. It's just equal to 0.1 kilogram meter squared. That's convenient. Yay me, right? Yeah, that's good. And then you throw this kilogram lump of clay onto the edge of the wheel, and so my I initial is equal to zero point 0.1. My final is equal to zero point 0.1 plus, however, whatever the moment of inertia of this lump of clay is. What are we going to treat that thing like? A shape or a particle? A particle. And we know that why? Because the axis of rotation is outside of the object. Thank you. Plus m, which is mr squared. The mass is 1 kilogram. The radius, not the radius of the clump, but the radius of the wheel is 0.5 meters. I don't even give you the radius of the lump of clay. So that's 0.1 plus 0.25 equals 0.35. All right, so now I'm ready to find the speed of the wheel. I say that L initial equals L final. That's just the angular momentum is the same, it's conserved. That's I initial, omega initial equals I final, omega final. 0.1 times omega initial is 3 revolutions per second. Remember on this, with the conservation of angular momentum, I don't have to put it in radians per second. The units will work out. And then I final is 0.35 times omega final, and then I solve that for omega final. So that's 0.3 over 0.35. I get 0.85, or 0.9 revolutions per second. Good problem. You're going to have one like that. There's one on almost every exam, so you'll definitely see one. Probably see one like number 7. Probably see one like number 6. Might see one like number 8. I don't always put those on there, but sometimes I do. Yeah.
Number 6.
Number 6? Oh yeah, so number 6. Number 6 looks complicated because there's a lot of words and the figure is a little wonky, but if you think about drawing this more simply, I'm just going to draw it as a bar that comes out of the elbow. That means that the axis of rotation is right there, and then there are 2 forces that act on this. There's a force right here, I'll call that FB, and then there's the force right here, I'll call that FW. This distance is 0.03 meters, and then this distance right here is the 0.35 meters. So whatever torque is caused by the bicep should also be caused, or should be balanced by the weight of the bowling ball. That's what does it. You could try to find what's counterclockwise and clockwise and say the sum of the torques is equal to 0. But in short, we want to say that torque B is equal to torque W. The torque of the bicep is equal to the torque caused by the weight of the bowling ball. So that's going to be the force of the bicep times that distance, 0.03 meters. Your bicep is attached to your forearm about 3 or 4 centimeters from your elbow, is equal to the length of your forearm times the weight. That's going to be 50 newtons times 0.35 meters. And then I solve that for FB. 50 times 0.35 divided by 0.03. That means in order to lift this bowling ball, which is pretty heavy, right? But in order to lift this bowling ball, my bicep has to exert 580 newtons, 10 times the weight of the bowling ball. Because notice the moment arms are 10 times different too. A really big force required to lift something that's, moderately heavy. 10 times. Your bicep works on a class 3 lever. Y'all probably learned different classes of levers, right? In 9th grade physical science. It's a class 3 lever. So you need really big forces to even exert a small force at the position of your hand. Okay? What else we got? Yeah. Number 4 in 2017. This one, 207, that one. You can probably tell by the way that I'm reading it so much that I haven't read it in a while, so you can probably guess something about the quiz. But okay, not a complicated problem. I have this solid metal sphere, and it has this radius of 2 meters and mass of 3 kilograms, but none of that matters, right? Because I'm actually rotating it about an axis of rotation that's here. So if I want to know the moment of inertia, it's just going to be equal to mr squared. I'm treating it like a particle because the axis of rotation is outside of the object. I'm not treating it like a sphere. That's irrelevant, that it's a sphere. So I know that this distance is 6 meters and the mass is 3 kilograms. So it's going to be mr squared, or mb squared, I guess I called it here. So the answer should be A. Yeah. All right. But again, y'all see me? Okay. All right. What else? Yeah. Number 4 from 22. Oh, that's 21. All right. Number 4, you said, right? I had a espresso in Dr. Rashin's office this afternoon. I feel kind of, whoa. Y'all too? Do y'all feel that way? Y'all feel tired, don't you? Why do we have this stupid quiz tomorrow? So I want to know the moment of inertia, right? First, is the axis of rotation central, or is it, outside of the body? The axis of rotation here is outside of the body, except for this body, it's internal to that. But I don't give you any other any other dimensions on these objects either. That's another clue that I'm going to treat these like a system of particles, because I don't say, well, the radius of these spheres are such and such, and the length of the bar is such and such. I'm just giving you the distance that they are from the axis. So the moment of inertia of this particle is equal to 0, because r is equal to 0. The other two, I need to find that moment of inertia. It's going to be, the moment of inertia will be equal to mr squared plus mr squared. That's going to be 4 times 3 squared plus 5 times 2 squared. 36 plus 20 is 56. It's a system of particles. That's the way you'll treat it. All right, what else? Y'all okay with these ranking problems? I like those. Y'all like those too? Yeah. So remember, on the moments of inertia ones, you're looking at which one has the most mass at the biggest radius. This one's relatively easy. The most mass gives us B as the maximum, so it's either A or B. A is definitely the smallest because most of the mass is really close to that point. Actually, no, is that right? Yeah, that's right. Because A and B are not equal to one another, so I know the answer has to be option A. Let me just repeat what I said there. So D is definitely the biggest because it has all that mass at really big radii. That gets rid of that one, and it gets rid of that one too. C is next because it has, this mass at this radius, which is about half the total length. And then A and B, well, they're either different or one's bigger than the other, but they're definitely not the same because there's no symmetry between those two. So I can say that the answer has to be B. And then, I could think about, is B bigger than A here? But I don't really need to because that's the only option that's left.
And how would you tell, like in a case where they're close together, which one?
Where B and A, like why is B bigger than A? I would say actually that A is bigger than B, right? Because I guess I never really thought about this, but yeah, the A is bigger than B. So the distance from here to here is bigger than the distance from here to here. So So, yeah, I would actually say that A and B are switched in that way. Yeah, I don't know. I don't know if that was on the test, on the quiz. It might be. But if it is, that's the answer is B. I'm not going to take it off. I've already printed it. I'm not going to tell you either. But you can whittle them down in the way that I did. You understand what I'm saying there? I don't remember if I put this one on the quiz. I know I did put one similar to it, and it might have been this one. But I'm not going to take it off because I've already printed them all. I'm lazy. Okay? Is that okay? Y'all get it right if you get it on the quiz? Yes? Yes? Yes is the right answer. Okay. You understand what I'm saying about why those are different? Okay. What else we got? Yeah, Tyrese?
Ball, number 10 or ball 14.
Ball 14, number 10? Sure. This one, this 500 kilogram car one? Yeah, that's chapter 7. So we're not going to see that. That has to do with centripetal force. If you remember, that was the one we did back in chapter 7 where I had a car that goes around a corner and I have to find the centripetal force, and that is equal to my static frictional force, which is mv squared over r. We did one of those, like, you'll probably forgotten because it was back before the other exam. But forgotten about those? Yeah, don't worry about it for the quiz tomorrow, but it'll come back for the exam. We'll read it. Okay, okay, yeah. On the same exam, number 15? Okay, yeah, I like these questions too. I mean, I know y'all do too. But where you have a bar and I have a flywheel, and they're either spinning or not spinning. In this case, the bar is spinning at 3 revolutions per second, and the flywheel is not spinning at all. So this thing, the bar is spinning around, and the flywheel is just sitting there stationary. And then they come together, or they engage in some way. I like to think that the bar is actually sitting on top of the flywheel. It doesn't have to be. Like, it can just engage by a series of gears or whatever. The point is that they engage together, and then they start spinning in the same angular velocity. This is similar to the questions that we've done before back in chapter 6, where I had 2 objects that have a certain velocity, and then they stick together and they move off at the same velocity, that perfectly inelastic collision. Very similar to that, except now they're rotating, and I have to consider the angular momentum. So I say Li is equal to Lf, the initial angular momentum, is equal to the final angular momentum. That's going to be I1 initial omega 1 initial plus I2 initial omega 2 initial is equal to I final omega final. Now, this is omega 1, this is omega 2. Initially, I1 is 2 kilogram meters squared. That's the moment of inertia of the bar, times omega 1, which is 3 revolutions per second. This value is what? What's omega 2I? That's the angular velocity of the flywheel. It's 0, right? It's not moving at all. And then that's equal to I final. I final is going to be the sum of the 2 moments of inertia. That's 2 plus 4, which is going to be 6. So that's 6 kilogram meters squared times omega final. And then I solve for omega final. That's equal to 1. So what I did here to get I final is I just added the moments of inertia. That's just like what we did here when we did those perfectly inelastic collisions. We added the masses of the 2 spheres because they stuck together and then they moved off at the same speed. So to find their inertia, we just added their masses. To find the total moments of inertia, I just add the moments of inertia. So very similar to that problem. All right, what else? Yeah? That's it? You sure? You feel okay with the quiz tomorrow? Feel okay? Remember, if you have had all perfect scores on the quiz, it doesn't mean anything. Take the quiz, I'm going to drop your lowest score, but I'd encourage you just to take it, just for fun, you know. You don't have to prepare for it. Just to help you sort of think about the upcoming exam. Because this is the big bulk of the exam. Chapter 7 and 9 are smaller parts of that exam, or at least less difficult parts of the exam. So this is the big bulk of the exam in a week or so. So it's good prep for that. All right? All right, hold on, don't leave. I know a couple people meandered in, so as you're walking out, just make sure I got your name. Was it 26